Record. Awesome. All right, cool. Thank you. Yeah, I can't move that out of the way. All right. Good. Welcome, welcome, welcome. This is one of my favorite classes to teach. It's just a pleasure to see so many of you interested in genomics. It is the best time to be in genomics. The field is just exploding. And that's what we thought 10 years ago. We thought we had reached the peak and it was going to be awesome for a few years, and then it was going to be, yet another field went by. But no, genomics has continued to just explode. And the new technologies have simply made it ever more exciting. In fact, just this morning I was talking about one more topic we were going to add at the end of the term about pharmacogenomics. Who's interested in pharmacogenomics? So that's basically tailoring drugs to people and repurposing drugs through massive data processing, which we're going to somehow squeeze in with the last lecture at the end here. Lecture 22 is now going to have one more cool topic. All right, so here we are in the middle of aligning and modeling genomes. We're in the second lecture of module 1. And today we're going to dive deeper into alignments. We looked at global alignment on Tuesday. Today we're going to be looking at local alignment. And then we're going to define linear time alignment. The perhaps the most well-cited algorithm in computational biology, 15,000 citations. The BLAST algorithm. We're going to have a BLAST, talking about BLAST. And then we're going to talk about the probabilistic foundations of sequence alignment. And then a very cool, slightly esoteric topic about deterministic linear time string match. So first of all, we're going to recap a little bit of that lecture 2 from the plane and talk about this duality between paths through matrix and alignments. So who's like 100% with me on this one? I'm going to describe the topic and then you're going to raise your hands if you're 100%. So basically the concept is that as we go through from the top left to the bottom right, if I move to the bottom, I introduce a gap here and a gap there and a sequence here. If I move to the right, I introduce a gap in this sequence and a letter in that sequence. And every time I move diagonally, I pick up a letter from both sequences. And when I end up at the bottom, I have a path through this matrix, which gives me a one-to-one mapping to a complete alignment between the two sequences. Who's 100% with me on this concept? Then there are, an exponential number of ways to go through this matrix, just like there's an exponential number of ways to align a pair of sequences together. And then the score can be computed in a quadratic fashion by simply taking the maximum of these 3 options in any kind of traversal of that matrix that has the top left and top left available, giving me the top score at the bottom right. Everybody cool with this concept as well? And once we remember these choices, once we've saved these choices, we can then use that to trace back from that optimal score to basically figure out what are all of the choices we made along the way giving us that optimal score. And that's the trace back part. Everybody with me here? Awesome, good. So we sort of looked at the concept of having only local update routes, and that was crucial. And the reason for that was that we really wanted to have a constant time computation rather than have to look at something linear for each one of these n-squared positions. We were able to compute this by, making a choice between a gap in one direction, a gap in the other direction, or a match/mismatch. The score here could be as simple as 1 minus 1, or it could be more complex by having a full matrix of computation here, as we saw in the Excel spreadsheet. And then we're able to compute the scores of increasingly long prefixes reusing our computation. And then we frame that in the concept of sort of this 5-step recipe for dynamic programming of having a parameterization of your matrix, making sure that the sub-problem space was finite, choosing your traversal order, defining your recursion formula, and then remembering this choice. Okay, everybody cool with me? Okay, And then we looked at two variations. One of them was this bounded dynamic programming concept that if we traverse too far to the right, we're going to be paying too big of a penalty. And if we traverse too far to the bottom, we're going to be paying too big of a penalty. And then the penalty to recover towards the diagonal would be simply so large that it's unlikely that true optimal solutions in real biological sequences would be going through these spaces. So in the practical case of aligning sequences that are pretty similar to start with, we could exclude these off-diagonal items as a heuristic, no longer giving us a deterministically optimal solution, but allowing us to bring the computation from n squared to kn, which is effectively linear in the length of that sequence. Everybody was cool with that? Somebody just emailed me a few minutes ago saying, hey, could you review the linear space computation? Who thinks that that's a good idea? Good. See, every time you think of asking a question, just realize that there's another 30% of the people out there who are wondering the same thing and are just too shy to ask. So never be shy to ask a comprehension question. Okay? All of you guys are ridiculously smart. I'm just honored to be here lecturing. If you don't understand something, it's not your fault. It's my fault. So never, ever be shy to ask. Okay? Good. So what is the linear space computation? So basically, in terms of finding the optimal score, it's trivial, right? Instead of just traversing diagonally or some weird, funny fashion, we just traverse column by column, and we only save the last column, giving us the bottom right optimal score in linear space, linear time. Everybody, oh, sorry, quadratic time, linear space. Everybody cool with that, right? The less trivial part was how do we actually get the path with only saving one column at a time? And the way we did that, and we're going to review that next week when we talk about hidden Markov models. We're going to look at the forward algorithm and the reverse algorithm, which are symmetric to each other. Each of them is basically calculating the exact same thing of that score. In fact, let me start by saying I could calculate the optimal score of aligning two matrices by, instead of looking at prefixes of increasing size, by looking at suffixes of increasing size. I could start at the bottom right, calculate the suffix of length 1, suffix of length 2, suffix of length 3, all the way to suffix of length n and m, right? I can just reverse the computation, carry out the exact same scores from the bottom right to the top left. Who's with me on that one? Right? It's reversible. Some people are not with me on that one. So raise your hands and ask questions. It's not with me. Who has a right arm? Come on, you're shy. I know you have one. Let's try again. Who has a right arm? Honestly. There you go. Good. Now, from the people who have right arms, any questions on this one? No. Okay, good. So you're with me. You're just shy to raise your hand. Just look puzzled. And then I'll know. But anyway, basically, I can compute that score either way. And the beauty of this computation is that if I compute the score from here to there, it basically gives me the optimal score of aligning the entire sequence here with with the prefix here to any prefix here. So basically, over here, I have the score of aligning this prefix with the prefix of length 1. Here, optimal score of aligning the same prefix with the prefix of length 2, and all the way down here. That basically means that I have the optimal scores of aligning half my sequence with all possible prefixes of the other sequence. In here, I basically have all of the optimal scores of aligning the second half of that sequence with all possible postfixes of the second sequence. If I add this column and that column, that gives me the score of aligning, anything that ends here and anything that starts here. And therefore, if I sum up these two columns, I effectively get the exact score that I can possibly get through any one of these points. And then all I need to do is pick the maximum among all of them to basically know how I'm traversing the entire sequence. Okay? Yes. Speak up a bit. Oh, I see. Choose a different cursor. Let's see if I can do this. All right, I'll try this. Okay? Any other questions? Everybody with me so far? So basically, if I add up this column and that column, that basically gives me the score, the maximum score, ending at any one position and then picking up at the same position. Okay? And here's where, so basically, up until here, we've just increased layers of complexity. And now the last part is basically saying, I have now the ability of choosing among all of these vertical things, which one is the maximum one that gives me the maximum score. So that basically means that if I go through these sequences, this is the place where I get the optimal traversal. And once I have that, I can just simply skip all of this. I know that the optimal alignment is going through that point. I don't have to compute the other two halves. Okay? Everybody with me? The two quadrants, the upper right and the bottom left quadrant, I can just ignore it. Who's with me on this one? Yeah? Good. So that basically means that I only have to recurse in these two quadrants. And when I recurse in these two quadrants, I find the midpoint, and then I can just get rid of that quadrant and that quadrant. And here I can get rid of this quadrant and that quadrant. And that's where that recursive computation of, 1 plus a half plus a quarter plus an eighth comes in. Okay? Think of it as a turtle basically going from one point to the end. It traverses half, 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 half. It will never actually get there. Okay? And that's why it asymptotes only twofold more work while still keeping the linear space computation. Awesome. I see a bunch of people nodding. Yes? No. Basically, in order to find this, all I computed was, all I computed was this part, not doing this, and this part, not doing that. Sounds good? So basically, each time I only do one matrix, and then half, and half, and half, and half. So basically, okay? It's kind of a cool algorithm. I think it sort of helps you think about things differently. And then this was my glorious Excel moment. My wife will be so proud. I did not, frankly, know how to use Excel before. I just Googled each of the functions. I'm like, it must exist. So, I use Excel for sorting and for summing. And I do averages too. But anyway, I can now do alignment. And then here's just another cool example where basically you have two separate paths, giving you the optimal score. I had to fiddle with the sequence to actually make that happen. But fiddle with it, it's kind of fun. And then here you can, of course, change the scoring matrix without any extra penalty. You can make as interesting things as possible. In fact, later in the lecture today, if we ever get there, we're going to talk about the diagonal items and what they mean here. Okay? So that's the review of last time. Any questions from last time? Okay, good. So that was global alignment. I had to start at the top left and I had to finish at the bottom right. But local alignment basically means I can align subsets of the sequence. So I don't have to start at the top left and the bottom right. So local alignment is defined as an alignment of a substring of S with a substring of T. So why local alignment? Because sometimes a small domain of a gene may be the only conserved portion. Or I may be looking for a small gene in a large chromosome. And we're going to talk more about that later in this lecture. And then also, large segments can actually undergo rearrangements. So basically, I may end up with something like this, which is equivalently seen as something like that. So A, B, C, D are basically 4 segments here. And then in one sequence, A, B, C, D was in order. In the other sequence, it was flipped to B, D, A, C, which can also be visualized as such. Okay? So if I enforced a global alignment, I would only get part of it. Which parts would I get? Raise your hands or just call them out. Either BD or BC or AC, and that's about it, right? Basically, it would have to go through here or here, or here, right? And that's not satisfactory. So the reason for doing local alignments is you can say, well, there are truly 4 local alignments, and then I can use them as part of figuring out the rearrangement. Everybody with me here? So that's why local alignment is important. So how do we transform the Needleman-Wunsch algorithm to the Smith-Waterman algorithm? So what do I need to do? So Needleman-Wunsch had initialization at the top left. Where do I initialize now? Anywhere. Needleman-Wunsch had termination at the bottom right. Where do I terminate now? Anywhere. And then the iteration had only 3 options. What options do I have now? Yeah, I could just restart anywhere. Okay. So basically, I can initialize anywhere. I can stop anywhere. And then I can always choose 0 as my starting point. So basically, if I get a negative score, you know, forget it. I'll just choose 0. You remember in some of the alignments that we saw previously, we had gone to quite negative score before actually picking up and gaining some traction. Here we would just say, I'll just start here. Sounds good? All of the good, none of the bad. Okay? Everybody with me? So that's what Smith and Waterman did. Now this is, everybody knows local alignment Smith-Waterman, when in fact Needleman-Wunsch is the original algorithm. Anyway, so what about semi-global? Semi-global basically says that I don't penalize end gaps. So sometimes as I'm sequencing a genome, I want to make sure that every part that I have is aligned, but I know I may not have the whole thing. So I don't want to penalize for, you know, a chunk at the end missing. So how do I do that? Yes, good, without the 0. Do we have the scribe for today, by the way? All right, we're recording it for the scribe. So that basically means I can initialize either at the top row or on the left column, anywhere. I can terminate at the bottom row or on the right column. And then, you know, I just get rid of that 0. Okay? So you can basically come up with your own variations of this. But, you know, it just, once you have the methodology, you can figure it out. So we talked a little bit about, yes. Good question. What do you think? Anyone else? Yeah. No? What do you guys think? Yes. Exactly. You just go through the matrix once. It's n squared. And once you're done, you can just search everywhere, which is also n squared. Right? Yeah. Once you figured out the optimal point, you just trace back to wherever you want. Basically, and then wherever you want basically means that 0 that you're going to find. Basically, if you have a 0, you'll have one of the 3 options is going to be top left, you know, top or left. And then the 4th option will be 0. And then as you're building your local alignment algorithm, you can choose to not stop at the 0, even if you have a 0 option, to make a maximum length local alignment. So basically, the local alignment that gives you the best stopping position, but also is as long as possible. You can go through regions of negativity and then go back up. Does that make sense? Good. All right, so we talked a little bit about sort of varying gap penalties. If I were to come up with a generalized gap penalty function that basically searches through, you know, the top left, including a character in both, or just a gap of any size, what I would do is choose between, you know, taking that diagonal or any of the optimal gaps. And my gap scoring function is just simply a function of that length. So basically, what I need to do is choose among all the possible options for that column and for that row that give me, that score that I had before for any of these positions, and the gap penalty, which is now a generalized gap penalty of length I minus k or j minus k, depending on whether I'm on the column or the row. So this now has changed, the running time to what? So I still do n squared. I still fill up n squared entries, but for every one of these entries, now I don't have a constant time algorithm. What do I have? Linear. So that basically makes it a n cubed. Okay? So basically, I can just code up a generalized gap penalty function by, paying an extra order of order of growth. Okay? But then we don't have to be so general. We could come up with gap scoring functions that are intermediates. So we talked about the linear gap penalty, which simply basically says I'm going to pay the same penalty regardless of how big my gap is. You could have a quadratic gap penalty that basically says, initially I'm paying a big cost, but then as I increase the length, I pay smaller and smaller costs. But that, as we talked about, is much more expensive because I have to code it up as a linear search for every one of these entries. Or I could have an affine gap penalty that approximates this, that basically pays a fixed cost as soon as I open a gap. 0 has no cost, gap 1 has a fixed cost d, and then every additional nucleotide that I add, once I've paid the cost of opening a gap, has a smaller penalty. And then to achieve this, all I need to remember is whether I'm starting a gap or whether I'm in the middle of a gap. Okay? So that means that I'm introducing something known as state. And we're going to talk about state when we talk about Markov chains and stuff like that. So the state of that sequence effectively simply requires an additional matrix that I'm going to be filling in. And I'm going to have to remember where I'm in this matrix or in that matrix. Okay? And then switching between the two matrices is going to happen whether I'm starting a gap, I'm now in the gap matrix, or when I'm done, I'm closing the gap, I'm back in the not in the gap. Okay? So that is something that we can look at in recitation, but it basically allows you to approximate something like this without paying an order of growth in the runtime. Okay? And then the last one is if I want to have gaps that are length 3, pay an increasingly large penalty, while gaps that are that are not length 3, or gaps that are length modulo 3, gaps that are modulo 3 pay a smaller penalty. And then the reason for that is because within protein coding sequences, if you add a gap of 3, you're only losing one amino acid or gaining one amino acid. Whereas if you add a gap of 2 or of 1, modulo 2 or modulo 1, then you're changing the reading frame of translation of the entire protein, and then the protein becomes nonsensical. Okay? So this is actually very helpful biologically because it conserves the reading frame of translation. Yeah. Yes, absolutely. So you can basically have 1 plus this. And in fact, this is exactly what I'm showing here, basically. That initially I pay this big penalty, and then, sort of you see the offset is there. And then, again, you just add more state. And the possible states are either I'm starting a gap, or I'm in mod 3, or, sorry, mod 3 equals 1, or mod 3 equals 2, or mod 3 equals 2. Cool. So this is variations on the same alignment technique. Okay? It's a quadratic alignment technique, and then we can tune it to our preference for all kinds of things. What we'd like to do now is go way, way faster. And going from n squared to order n means that instead of taking a gazillion years to align a whole human genome, going to do it in milliseconds. I mean, it's actually that bad. So basically, a factor of 3 billion is the difference between years and seconds, right? So if I want to align a sequence to the entire human genome, I can just choose my n-squared algorithm and basically search for, this times 3 billion, or I can choose a linear time algorithm. Okay? And again, as the length of the sequences increases, you're looking at 3 billion squared, and so on and so forth. So what we're going to do is look at first a probabilistic way of doing it. And then at the very end of the lecture, we're going to look at a deterministic way of doing it. Okay? So linear time string matching is basically when I'm looking for exact matches of a pattern with no gaps. And the Karp-Rabin algorithm basically gives you a probabilistic linear time, which basically means it's linear if you're not terribly unlucky. Okay? And then the way to do that is to interpret your string numerically. And we're going to start with a broken version of the algorithm, progressively fix it to make it work. And then, we're going to look at actually the Z algorithm at the end. So what the Karp-Rabin algorithm does is that it basically says, if I'm trying to align, 2, 3, 5, 9, 0, 3, 1, 4, 1, 5, etc. If I'm trying to find this string called the English letter P, not to be confused with the Greek letter. If I'm trying to find my pattern in my text, how am I going to do this faster than searching every character? I've told you the answer already. Yeah, interpret numerically. What does that mean? Yes, consider as numbers. What does this mean? Yes. Speak up, speak up. Good. Everybody sees that? So that basically means that instead of strings, I'm going to think of them as numbers. So every single one of them is going to be a number, right? So then all I need to do is check whether the number y7 is the same as the number x. Okay? And if the two are the same, that basically means that the strings are the same. Who's 100% with me on this one? Awesome. Who sees the flaws? 2 people, 3 people, 4, 5. Okay. So here's the code. I'm computing x, and then for every position, I compute y, and if x equals y, I print the match. Okay? Sounds great, right? This doesn't work. So why doesn't it work? So 3 hands, 4 hands up. Right. Why doesn't it work? Different frames to compute with? Yeah. Okay. Yeah. Okay. You had an answer? Okay. Anyone else wants to share an answer? Right or wrong? Yeah. It requires it to be exact. Okay. Yeah. So where's the hidden computation? Exactly. Compute y. That's a linear operation. It's not a constant operation. You have to actually compute it, right? So, so how are we going to fix this? So to make it work, what we're going to have to do is compute the next number based on the previous one using constant time computation. How can I do that? So I want to make this constant time, and I'm going to use the previous one. Yes. Number 1, shift the frame. Number 2. How do I shift the frame in decimal? Multiply by 10, right? Shift the frame. What else? I've shifted the frame. So instead of having, I previously computed, say, 23,141, and I now want to use that to compute 31,415. Yes? adding the lower decimal, and then exactly remove the top decimal. Okay, so basically, so that does it, right? We're now order 1. Everybody happy? Good. Everybody sees this? Okay, now who sees the next problem? These numbers can be pretty big, right? I'm aligning a gene of like, 3,000 nucleotides. And I suddenly have 3,000 digit long numbers. So what's the problem? Exactly. See? Yeah. So suddenly I have to pay some long way of computing. Basically, it's no longer so how can I fix that? Yeah. Beautiful, beautiful. So take the modulo. So if I take the modulo, then, I'm done, right? Who can see now that computation is actually constant because I'm taking the modulo. I'm basically just taking, say, the lower digit, the lower, the least significant digit, for example. All right, so what's the problem now? These 3 people who have it all the way back. Much better, much better. So instead of just cutting off my sequence, I'm going to actually define modulo, instead of the modulo being a decimal number like 10,000, which would be the lower digit, take the modulo like 9,999, and then you just use all the digits. Much better. Great. Now who sees the next problem? Yes. Collisions and false positives. If I take the modulo 9,999 and I'm comparing strings that are super, super long, I basically have, so many chances, one divided by the other, to basically have collisions. I'm taking a very large space, condensing into a very small space, and every time I see a match, I might have a collision, okay? So basically, what I need to do now is when I have a hit, I then go and compare the actual characters, okay? Everybody sees how we fixed the last problem? Who sees the next problem? Gosh, this one never ends. I have no more room at the bottom of the slide, so this will end. Yes? That's exactly right. The problem is that it's no longer deterministic linear. It's now probabilistic linear. So it will be linear unless I get really, really unlucky, right? So we basically now have an algorithm that runs in linear time if we're not super unlucky, okay? And this actually works. Good. So this is it in practice. We basically do the, I remove 3 times 10,000 and left shift. I add the lower digits and so on and so forth. And this is how we deal with the long numbers by hashing. And instead of hashing with, 2 to the m number, I basically hash with a number that's like odd. And that will basically utilize most of the digits. And, for example, I can take mod 13, happens to be my birthday. And then the bringing problems collusions. And then we deal with collusions by basically verifying that a hit is actually a valid match. And then the problem then is that the analysis of the runtime becomes more complex. We have to compute the expected runtime and include the expected cost of verification, and then show the probability of the spurious hits is actually small, and therefore that the expected runtime is linear, even though every now and then we'll get super unlucky and it will be quadratic. Okay? Everybody cool? This is kind of fun, right? Yeah. Then you just simply fall in this case of the algorithm, and you basically say, oh, this actually was not an exact match, and then it's a spurious hit, and I just continue. Ah, well, we're going to talk about that. Yeah, basically this is for string matching, not for sequence alignment. So we're going to talk about ways of doing that. So that's where the BLAST algorithm comes in. Okay. Oh, funny you should ask. All right. Do you guys feel like you've deserved your break? How about you stand up for your 40-second stretch? This is mandatory. Everybody has to stretch. You think I'm giving you exercise. What I'm getting is more calories going to your brain and more oxygen. Try hopping. See if we can get some synchronous hopping. So we're going to talk about the benefits of muscle on brain function by the end of the term. All right. Everybody still with me? So we talked about global alignment. We talked about local alignment. And then remember how I showed you this sequence that had A, B, C, D shuffled? What I can do now is use my super fast local alignment to basically search for patterns that are the same and then use these to form the basis for a longer alignment. And that's kind of like how the BLAST algorithm works, okay? So the problem it's trying to solve is not sequence alignment. The problem it's trying to solve is search. So basically sequence database search. And it assumes that the sequences have, so sequence alignment that we saw earlier, assumes that the sequences have some common ancestry. And then it searches to find the right alignment between the two sequences, and it has an evolutionary interpretation in terms of the minimum number of events. That's what we did in lecture 2. In lecture 3, what we're going to try to find is sequence database search. So given a query and a target, we're going to ask which sequences, if any, are related to the query, but the individual alignments did not be perfect. Once the initial matches are reported, we can just fine-tune them later by basically using sequence alignment, okay? All I need to do is find whether there are any matches super fast. So the query must be very fast for a new sequence, and most sequences will be completely unrelated to the query. So if I'm searching for, a part of the human genome, most of the human genome will be unlike that part. But then I want to search very fast, where does that part go? And once I know where it goes, I can spend the time to align it well, because then I'm only solving a very small problem. So we're going to exploit the very distinct nature of the database search problem of having many spurious hits. So we're going to do that by knowing that if you're going to be rejecting any match which is not very good, why would I bother building a full matrix to basically realize that it's just not good? Something that's very good is going to have to go more or less through the diagonal, right? So then I'm going to be able to sort of speed things up. And something that's very good is even going to have stretches that are perfectly identical. So now instead of using sequence alignment, I can actually use string matching for small parts of that string. So basically, if, for example, a sequence of length 100 is going to only matter to me if it's at least 90% identical, then if it doesn't have 10 nucleotides in a row, I can just outright reject it. So what I'm going to do is pre-screen sequences with common long stretches, and I'm also going to put the speed where I need it. Therefore, I'm going to pre-process the data, spend a long time pre-processing the data, because that's offline. But once the query arrives, I'm going to be able to act very fast. Okay? So the solution is to actually do something known as content-based indexing, which basically means that I'm going to index all 10-mers based on their own sequence, and knowing that only one 10-mer in 4 to the 10 will match, 1 in a million, even with 500 k-mers, only 1 in 2000 will match. So I'm going to get very many speedups. Okay. So this is the concept of the BLAST algorithm. Did I tell you 15,000 citations? I meant 50,000 citations. This is, the basic local alignment tool. If you write such an algorithm, you're like, wow, I did it. So you can probably rest for the rest of your life and just, get royalties. Joking. But instead, these guys basically said, oh, a year later, they're going to write, or a few years later, they're going to write the gapped BLAST. And guess what? It had even more citations. So I don't know. I would have stopped at the first one. So this is the numbers of citations per year, and holy gee, it's still high up there. So there's two key insights that made these algorithms so awesomely great. So one was hashing, just like Karp-Rabin, semi-numerical string matching. Okay. The other one is very, very cool. It's a neighborhood search. And that basically means that even if there's no exact k-mer, I will still be able to find a match. Okay. So let's look at how it works. So what the BLAST algorithm does is that it splits the query into overlapping words of length W. So it basically takes a big query and it says, I'm going to search these three, and those three, and those three, and those three. Okay? And it does this for overlapping sets of three. Everybody cool with this first part? Yes? And then it's going to find the neighborhood words for each of those. So we're now in protein space, and I'm going to have to find things that are almost like PQG. So I'm going to search through my amino acid similarity matrix for things that are similar to PQG. And if I have the exact match, it's going to be a score of 15. If I have an inexact match with PEG, it's going to be 15, and so on and so forth. Okay? Everybody cool on the neighborhood search part? It's a very, very cool idea. It basically says there are only so many amino acids. Let me just search their neighborhoods. Okay? And then until some threshold T. And then I'm going to look up in some table where those neighbors are. And I'm going to get my seeds, S, with which I'm going to be searching my database. And that basically says that when I was searching PQG in this sequence, it basically took me to PMG in the other sequence, which is close enough. Notice I didn't even have one exact match. And then what I'm going to do is that I'm going to extend the seeds until the score drops off. I'm now taking the original sequence and putting it here versus my database, and I'm just searching for a match. Raise your hands if you're with me. Awesome. Raise your hands if you're not with me. All right. So any questions, even from the people who are with me? Louder, please. Yeah, so you're basically asking why the speed up. Let's not worry about that yet. Let's just worry about whether it will work. So basically what we're trying to understand is why this even makes sense. And then we'll worry about the speed up in a minute. But basically why this even makes sense is because when I'm trying to find a match to a sequence, I'm going to basically be exploiting the nature of the problem that, well, if this is going to be a good match, there will be at least some portions that are very good matches. And I'm going to be searching for those portions really, really fast by using hashing, by using exact matching. And this actually addresses your question of, what if it's not an exact match? Well, I'm first going to expand the neighborhood and then search for exact matches of that neighborhood. Who can see that these cool ideas sort of coming together? It's, oh, yeah, that kind of makes sense. Any questions for, yeah? Yeah, that's a problem. Basically, if right after that it picks up again, then because you're searching your entire sequence, you're going to have another seed that starts right after. So you're going to have 2 hits. And in fact, one of the better versions of BLAST is 2-hit BLAST, where you can basically say, I'm going to require that at least 2 different portions match. And that actually immediately addresses your problem. Yeah. A word neighborhood basically says that so the whole concept is that instead of sort of only matching the exact set of amino acids, I'm going to search for amino acid strings that are almost as good. In other words, if basically says, instead of basically aligning everything and seeing what is high scoring, what I'm going to do is figure out what would be high scoring to start with. And then instead of waiting until I align them to basically see, oh, that's not too bad of a mismatch, I'm going to tolerate it. I'm going to say, what are all the things for which I would say this is not as bad, so I will tolerate it? And then just search for those things in an exact fashion. It sort of flips the series of operations around. Instead of basically first aligning with some threshold, I'm going to look at what would align to that threshold and then search for perfect matches to the things that would align within that threshold. Any other questions? Yeah. Yeah, so that's, I think, the same essence as your question. So basically, the big question is, how do we choose the width of the word? How do we choose the length of the word? How do we choose the threshold t? How do we choose, the x of the drop-off? And all of these are parameters, and they're tunable. If I make my word very, very long, I'm going to have many fewer hits, and it's going to go much faster. But I might actually miss many. I'm going to have fewer false hits, but I'm also going to have fewer true hits. So it's a balance. This was a good balance for this slide, but in practice, you're going to be using maybe W of length 5 or 8 or something like that. And in amino acid space, this is actually pretty big because it's an alphabet of length 20. In nucleotide space, it's not as big. It's not as good. But in amino acid space, 3 is actually not so bad. 5 is even better. 8 is actually very stringent. Yeah. Well, that's the next part of the lecture. It's coming. Okay. You could overlap them if you wanted to. Basically, because you're searching really, really fast, you could even just not bother overlapping them. You could just say, I'm going to search one here, another one here, another one here, another one here. Basically, what you're trying to do is find these hits, and you're going to have so many opportunities along that sequence to find those hits. Okay? Who thinks BLAST is kind of cool? Right? Awesome. Perfect. So, why BLAST works? Well, the first part is that by pigeonhole principle, if you only have, okay, the pigeonhole principle basically says that if you have 2 pigeons and 3 holes, there must be at least 1 hole with no pigeon. So basically, no matter how you partition your pigeons into holes, you can't possibly cover all the holes. Why is that relevant here? Because if I have 10 mismatches to spread into a sequence of length 100, there must be at least a stretch of 10 nucleotides that has no mismatches, because there just aren't enough mismatches to go around. And if I spread those mismatches randomly, I'm actually going to be much more lucky than if I spread them in the worst possible case. In the worst possible case, I'm going to have a length of 10. If I spread them randomly, I'm going to have much longer length. And if I spread them biologically, I'm going to have even more long stretches. And the reason for that is that biologically, you have portions of a protein that are well conserved and portions of a protein that are not as well conserved. And the reason is simply evolutionary importance. So basically, some things, their function is conserved, and those things, when you search for them, you're going to find extremely good conservation. Basically, conservation is not partitioned uniformly, and it's not even partitioned randomly. It's partitioned in an extremely biased way, where some stretches are extremely well conserved and others are not. Is everybody with me here? Yeah, absolutely, absolutely. BLAST is one of the core algorithms for genome with mismatches. Okay. So again, beyond W-mer indexing, so what we'd like to do is be either faster or better sensitivity. One idea is to filter low complexity regions because they can cause pure hits. For example, if I have and in my sequencer Q, which are these aggregating amino acids, I can just throw them away because they're going to match all the time. The other thing I can do is I can build my database of basically all the places where I find, every stretch of 8-mers. Okay, so basically, back here, I'm building my database offline. So I basically just, scan through my entire sequence, and I say, every time I find a particular, string, I can just index all the places where I find that string. And then what I can do is, if I find a string a lot, if I rank all of the strings based on how often they were found, I can just throw away the ones that were found very often. It's a little counterintuitive, right? Well, that sequence appears to be very common. Why would I throw it away? Well, precisely because it's very common. That basically means that the most overrepresented items in your database are also the ones that are likely to be spurious hits. You don't care about those. In fact, these are sequences that just don't give you that much information. If something is very common, the level of surprise when I see it is actually very low. The level of surprise is the level of information. Basically, they're actually quite uninformative if they're very frequent. And just toss them away. The other idea was actually your idea of, hey, what if the sequence drops off and then picks up again? Well, two-hit blast does exactly that. Instead of having one 8-mer, I'm going to search for 2 3-mers. And any one 3-mer is going to be very common. But 2 3-mers together, that's actually quite uncommon. So basically, 2 smaller W-mers are much more likely than 1 longer one. Therefore, it's a much more sensitive searching method to look for 2 hits instead of 1 with the same speed. And it improves sensitivity for any speed or speed for any sensitivity. And then beyond W-mers, I could actually hash with non-consecutive K-mers, known as combs. So then the key idea is, instead of searching for a 5-mer, I'm going to search for a 3 out of 5. Okay, so I'm going to search for the first, the third, and the fourth character. And then indexes is the same, only for each column we're storing, the list of positions in the database where it occurs, and then we perform the lookups to answer the query. And then the question is how to choose the combs, and the best answer is actually at random. So this is known as random projection. You're basically taking a very high dimensional space and you're projecting it onto a lower dimensional space, but you choose those dimensions randomly. I have a 5-dimensional space, and I'm choosing 3 of these dimensions at random, and I'm just projecting it onto those 3 dimensions, ignoring the other 2 dimensions. So I'm choosing the positions of star at random, and then I can analyze the false positive to false negative rate. And then when you do that, what you basically ask is, what is the probability of not finding a match? And then that's 1 minus that probability to the number of characters that I'm searching. And then if I repeat the process a bunch of times, then I'm effectively raising that probability to a power. And that basically says that I have very, very low chance of actually missing something. So my query, for example, could be having a mismatch from the database here and there. But if my comb doesn't include those positions, I'm just going to score a hit. Okay? So that's the idea that, hey, even if I don't have a perfectly contiguous sequence, if I search with combs, I'm just going to be able to, by chance, ignore the mismatching. Okay? Say it again. Every time I hit something, I will then extend it out. Is that what you're worried about? Basically, in the extension step, if I had a spurious hit, I will then, know that it's spurious when I'm catching. Was that your question? Okay, awesome. So we talked about global alignment, we talked about local alignment, we talked about linear string matching, and then we looked at this concept of, I'm going to search with mismatches by first extending the neighborhood and then searching for that neighborhood and then sort of putting that in the context of a lot of heuristics such as the 2-hit blast, hashing with combs, and so on and so forth. Now, let's go back to one of the questions that was asked earlier about where did these scores come from. So when I extended my neighborhood, I extended according to some funny function. Let's go look at that funny function. Remember here, when we extended, we basically said, oh, that's a score of 18, 15, 14. How do I get these numbers? Okay. where you get these numbers is something known as the block, sum, or this probabilistic alignment matrix. Basically, there's different ways of scoring the similarity between pairs of amino acids. Okay, so in nucleotide space, we basically previously said, oh, let's penalize, let's reward matches, and then penalize transversions here more than penalizing transitions. So we penalize transversions by -1, and we penalize transitions by -1. This was kind of arbitrary, right? We chose +1 of the diagonal, -half, -1, completely arbitrary. But when we do this in amino acids, you'll basically notice that our similarity scoring matrix is in fact very complex. So where do these scores come from? And the big question is, are these two sequences actually related? So what does that mean, that two sequences are actually related? That means that they're much more likely to occur on top of each other in an alignment if they're evolutionarily related than if they are just two random matches that don't have a common evolutionary origin. So what it's going to be is a likelihood ratio between two possibilities. One is going to be that sequences are truly related, and the other one is that they're aligned spuriously. Are you asking a question? Go for it. Aha. So what you're basically saying is, across evolutionary time, I can have things lining up on top of each other simply because their codons are similar, not because they're actually functionally related. Is that what you're saying? Yes. So ideally, our score should capture both. And at different evolutionary distances, different things will weigh more. At very close evolutionary distances, if something is simply under neutral selection, it's not being selected, one way or another, then you would expect things that are close in sequence space, in nucleotide space, to be more often aligned with each other. But as you go further in time, you would expect this random mutational process to have saturated, and the dominant effect coming from the true amino acid property similarity. Are you with me completely? Great. Very cool. That's exactly right. So basically, there's something called the BLOSUM 62 matrix and the BLOSUM 84 matrix. 62 basically means that I hand curated a bunch of protein alignments that were, on average, 62% similar. And then I made the BLOSUM 62 matrix. And then I hired a bunch of other people, and I aligned by hand a bunch of stuff that was at 84% similarity, and I made a matrix of amino acid replacement frequencies for sequences that are 84% similar. And the difference between the two has a component that's driven by exactly what you said. Yeah.
How would you obtain the sequences for that? Would you synthesize them?
Yeah. So that was one approach, what I described, the BLOSUM matrix was one approach. You basically said, hey, let's hire a bunch of people who are really good at aligning stuff by hand, and then use a word or whatever word was around, and add spaces in the right places. The other approach is a generation approach, where you basically say, you know what, forget this. What I'm going to do is evolve sequences forward. And I'm going to just replace amino acids as I go. And these are actually the PAM matrices. So there's two families, as I mentioned. There's the BLOSUM family of scores and the PAM family of scores. BLOSUM basically says I'm going to take things that already exist and align them. PAM basically says I'm just going to generate them and then look back at that process and see what aligns. What you're pointing out is that when I simulate something, I get out what I put in. If I put in biases, I'm going to get out the same biases. And that's absolutely correct. So the way that you simulate them is by looking at very closely related sequences and then extrapolating that out. But yeah, you're basically trying to include as few biases as possible. All right, so let's now talk about how to interpret these scores and then, what they actually mean. Okay, so these are two ways of generating them. Let's start looking now at how we interpret them. Yeah. I'd rather not answer. I can go on and on about it. All right, so I mean, it is a heuristic, obviously. Yeah. I think it was a rhetorical question. All right, so what should the alignment score represent? So it should represent the probability that two similar sequences are in fact homologous. And as I mentioned earlier, the likelihood ratio between two hypotheses. Hypothesis number one is that the alignment is due to chance, unrelated. And hypothesis number two is that the alignment is actually due to common ancestry, as in related. So what we're going to do is calculate the probability of observing an alignment according to each hypothesis, the probability of observing X aligned with Y given the unrelated model, and then the probability of aligning X with Y given the related model. And then the alignment score is going to be the likelihood ratio between the two. The probability that alignment is not due to chance is going to be the random divided by the unrandom, the related versus the unrelated. And then the score is going to be some kind of log probability. And then the beauty of this is that if our score is a log probability, then I can just simply take a bunch of logs for the individual amino acids, add up the logs, and that's the same as multiplying the probabilities. And then these additive matrices are doing exactly that. They are actually interpretable probabilistically directly. This is exactly what we've been doing all along. Basically, as long as these scores are the logs of the probability of being related versus unrelated, then as soon as I add the scores, I get a sum of probabilities. So here's the model for unrelated sequences. Assume that every position in the alignment is sampled randomly from some distribution of amino acids. And then QA is the probability of observing amino acid A. Then the probability of an n-character alignment of X and Y is simply the product of the probability of observing all of the characters in the first sequence and the probability of observing all the characters in the second. Okay. Why do I do this? Because if two characters are very frequent, like if two sequences are just very GC rich, for example, then aligning Gs with Cs is going to be very close to random because by chance, I would expect to align them on top of each other. So that's our unrelated model. It basically simply says that if I sample characters by chance, here's how often they're going to line up on top of each other. The model for related sequences is the probability of AB, of the probability that evolution gave rise to amino acid A in one sequence and B in another sequence, given that the two had a common ancestor. And that's the probability of an alignment given by simply the product of this joint probability of appearing together. So then, to decide whether it's unrelated or related, the principal way would be to look at the relative likelihood of the possibilities, the odds ratio between the related and the unrelated. And basically, one of them is simply the product of the joint occurrence of A and B given related, and the other one is how often would A line up on top of B if they're unrelated. And if I take the log of this big probability is the sum of the log of these guys. And therefore, if at every position I have this ratio as the score, that will basically give me an alignment. So this is exactly what you have in the previous matrix. So when you have score of that alignment is, and we talked a little bit about these BLOSUM matrices and then these PAM matrices. The PAM matrices are evolved from the bottom up, and then the BLOSUM matrices are by observing alignment. So here's the BLOSUM 62 matrix that I mentioned earlier. Notice that on the diagonal, matching an amino acid with itself has a variable score. Why would that be? Because if I match a tryptophan to a tryptophan, it's a rare amino acid. It doesn't happen very often. So observing it on top of itself is actually quite unlikely. Not because of the numerator, but because of the denominator. Because the probability of observing it simply by chance in an unrelated model is Q of W and Q of W, which are actually very rare. Okay? And then common amino acids, if I see them on top of each other, I'm just not thrilled. I'm not excited about it. So observing an I and isoleucine on top of an isoleucine, yeah, big deal. There's a bunch of them. Yeah. Yeah. So it depends at what evolutionary distance you're looking at. If you're looking at very close evolutionary distances, look at the nucleotide space and ignore proteins. If you're looking at very far evolutionary distances, ignore nucleotides and look at the proteins. Yeah. That would be a good idea. You could basically say, hey, I'm only going to pick seeds in places where the amino acids are rare enough. You could do that. Another way to do that is to basically simply try them all and then throw away the seeds that happen too often. Instead of from the start saying I'm going to exclude those, throw them all in your database. And when some of them are very common, just don't use them. Does that answer your question? Cool. Correct. It depends on the frequency in one species and the frequency in the other species. And the way to do that is to basically use QX from one species and QY from the other species. Who thinks they've learned something today? Awesome. Good. All right. So again, BLOSUM matrices, it was based on blocks of sequence alignment, whereas PAM matrices were based on building things from the bottom up. Okay? Good. Now for something completely different. If you guys are sort of at the brink of being confused, start looking at your email. If you think you can handle something like a little crazy, pay attention, okay? It's gonna be fun. First of all, in terms of comprehension, who's comfortable with today's lecture? Who feels that they got it? Raise your hands, because now's a good time to remember that sentiment of, stick to that feeling, and let's keep going, okay? Now, we're gonna basically search for deterministic linear time. So just because of that possibility of getting really unlucky, we're gonna develop something a little crazy. What we're gonna do is search a pattern in a longer string. I'm a little crazy to do this in 7 minutes. It normally takes an hour and a half. We're gonna search for a pattern in a longer string in a way that at every interrogation of a sequence similarity that we propose, we save a little note of whether this told us something more about the surrounding sequence, okay? For example, if I search the pattern ABA in this long sequence, and I find it here, and I also find it there, then I will somehow register that this is in fact the same as that, and therefore that my text itself has some internal redundancy. Okay? So it's basically a beneficial side effect of having compared these characters to start with. Okay? Is everybody sort of following this intuition? That every single time I search, is this matching here, and is this matching there, and is this matching here, and so on and so forth, I'm going to be learning something about the patterns of internal redundancy in that text. So once I've learned about this, I can then start extrapolating it to other places. So, so the naive string matching basically says, there's a sequence of length t, and there's a sequence of length p, and for every shift, I'm going to be checking if it's similar, and if it's identical all the way, I'm going to print, hey, this pattern occurs. And this is just an order n squared algorithm. But then the test operation in line 4 tests every position in turn. And if there's a match, it continues testing. So basically here, this is a linear time algorithm. So the running time is just the number of comparisons, the number of shifts, and the number of successful character comparisons, because I would be silly to continue comparing if I find a mismatch. So when I search this, if I get to the 4th character and there's a mismatch, I'm not going to search all characters, right? So this is the intuition to start basically saying that when I search ABA against this, I search A with B, I find a mismatch, I shift by 1. I don't bother comparing B and A. Everybody with me so far, right? And then I compare with A, it matches. A with B mismatches. And then that basically means that I can sort of, continue shifting over. And ultimately, the worst case running time is that we're going to simply test every position. If I have AAA with AAA, then I'm going to get matches here. Then I'm going to get matches there. I'm going to get matches here, matches there, matches there, matches there, and so on and so forth. Okay. So in the worst case scenario, I have a pattern that occurs at every position, and I'm going to end up with n squared. The best case is if there's no match at all, and I'm going to end up with linear time. Okay. What we're going to do now is exploit the patterns of matches and mismatches to actually always end up at the linear case. And then the idea here is that when I have a mismatch here, if I know the internal redundancy structure of the pattern that I'm searching, I'm going to be able to make bigger jumps than simply jumps of length 1. Okay? So if all the characters are the same, as soon as I have a mismatch here, so basically, it doesn't matter what this sequence is. As soon as I have a mismatch, I don't have to compare any of these guys because I know the internal redundancy pattern of my pattern. Okay? So then I can just simply compare that character. I find a mismatch, I start at this position. Who can kind of see this already? Raise your hands if you're like, oh, there's something there. So there's information gathered at every comparison, and that information can flow back and teach us about the internal structure of P. Okay? Now, if all of the characters are different, when I search, if I find matches, I don't have to try the next position. I know I can just skip all the way here, right? And as soon as I have a mismatch, I'm going to try the first position again. Okay? So that's the key intuition behind this. The key intuition is that in the special case where everything is the same, I can be linear. In the spatial case where everything is different, I can be linear. And if I can just figure out about how to extract the internal redundancy pattern of my pattern, then I can just be linear all the time. Okay? Here's the key idea. We're going to basically learn the internal redundancy pattern of my string by calculating a vector, zi, which at every position I basically tells me the internal redundancy of S at position I. In other words, if at position I have a prefix of length 1, which matches myself, then zi becomes 1. And then here, this basically means that my internal redundancy of S with itself is 3. That means that AAB repeats for 3 nucleotides. Okay? Here my internal redundancy is 2 because AA is found here. Who's with me on the Z vector? Raise your hand. The Z vector basically tells me how long of a prefix of myself do I match at that position. Okay? Then the Z box basically tells me what is the end of that internal redundancy. So if I have a Z of 1, the end of it is 1 character away. If I have a Z of 3, the end of it is 3 characters away. Trivial, right? It basically tells me just how far I have to go from that internal redundancy. And then that's the right vector that basically tells me the right endpoint for each of them. And then the left vector tells me where every one of them started, but the longest one. Okay? So at every position K, if I know my left and my right vectors, I know just how much of that substring is actually identical. And that's extracting, again, the internal redundancy pattern. The key to linear time deterministic sequence matching, string matching, is that we can compute the z vector, the right vector, and the left vector all in linear time. Okay? And that's basically by exploiting the partial results that we have created as we're making it. And then, simply doing the case analysis of if I'm inside a Z box, then I know that all of that is the same as all of this, and therefore all of that is the same as all of this, and I can extrapolate out. And, simply not have to even compute these because I already have. Okay? So once I've computed this in linear time, and for this, just look at the lecture notes, then what's really, really cool is that if I'm trying to match a new pattern to an entire sequence, if I can compute the z vector in linear time, I can just add a funny character that doesn't appear in either of the two strings in the middle, and then simply compute the z vector for the concatenation of the two strings in linear time. I see some people smiling and even laughing out loud. This is awesome. Because that basically means that as soon as I compute the internal redundancy between the p plus t vector, if anything is length p, I'm done. I have all my matches in linear time. Remember that great moment 5 minutes ago. All right, guys, so that's for linear time matching, global alignment, local alignment, linear time alignment, BLAST, probabilistic foundations, and then some really cool, crazy stuff.